Okay, so let's recall last time that we have make some notation about the submanifold derivatives. So the gradient of a function in this case, sigma n is a hypersurface in n+1, and we did note this n to be the normal vector field. Unit normal vector field on n, on sigma n. Let me move this a bit downward here. So this is actually, so if you compute the derivative on the submanifold, this is equal to the full derivative on the ambient space minus the derivatives on the normal direction. You project it to the normal direction. And for any vector field, compactly supported vector field, you can compute the divergence on the submanifold using the induced metric. So when there's a script of sigma, it means that you're using the induced metric to compute the derivatives. V of x, that's equal to the divergence in the ambient n+1 minus, again, the normal direction. So again, last time we have made a notation that we denoted d over dt, d over dt of f is equal to partial over partial t of f plus the variation in the mean curvature direction. So you're actually, when you're computing d over dt derivative, you're actually tracing a point in the normal direction. You are supposing that the flow is flowing a point in the normal direction and compute the directional time derivative in that direction. Right. So with these notations, let's do some computations of submanifold geometry and give us some other expressions of the mean curvature vector, which will be used later. So again, as a submanifold, you can locally write it as graphs. For small enough open neighborhood, you can write it as a graph, x, u of x in Rn+1. So locally graphical. Without loss of generality, you can suppose the first, you can suppose that it's locally graphical over its tangent plane at a point. So this x here is in Rn. So it's x1 up to xn. And then we use this as coordinate chart. Local coordinate chart on the submanifold and use these to compute the induced metric. So for the induced metric, Gij, that would be equal to delta ij plus uxi uxj. This is because d dxi is equal to ei uxi. So this is a n vector, and this is the n plus 1 component. When you take inner product, you get this. Any questions? Okay.
Scroll up a little bit.
Sorry?
I'm scrolling up just a little bit, please.
Okay. Yeah, if you, I'm scrolling too fast, let me know so I can scroll back. And to compute the mean curvature, we already have an expression, but we want an intrinsic expression. So locally, any variations, you can also express it as a local graphical expression. So for any eta compactly supported. So you can consider the graphical variation with the variation field V equal to 0 in the first n direction, and then graphical variation in the n plus 1 component. Locally, locally any variations can be written as a graphical variation. And now let's compute dv. This is the derivative with respect to the ambient metric. So this is the n plus 1 by n plus 1 metric. And then using the notation before, we want to compute the divergence of V. So we first compute dn of V, that is equal to n times dV. Recall that the upward unit normal. So let me move this a little bit first. Negative du 1. So this is the upward unit normal. Dot dv. This then gives you negative, and then 0 in the first n component, and then grad u, grad eta. So this is again an n plus 1 vector. Okay. So the divergence of V with respect to the intrinsic metric, with respect to the induced metric, is equal to, oops, this is the Rn plus 1 minus n x dn x vx. If you compute the ambient divergence of V, right, so differentiate the ith component with respect to xi, but the first n components are already 0, and n plus 1 component here is independent of xn plus 1. So you get 0 here. And then when you're taking the inner product of this n plus 1 vector with respect to the normal, you will get grad u, grad eta. This is 1 plus grad u squared without square root in the denominator. Okay. And also from the induced metric, you can compute the area form. D mu of the induced metric is equal to determinant of G. And of course, the area form of a graph agrees with that, which is square root of 1 plus grad u squared. So now we have the first variation formula. Let's rewrite it in a induced metric using the induced metric for the first variation formula. So this is equal to d dt of the area of sigma plus you are taking the variation field V, and we have computed in the first lecture. This is equal to the mean curvature vector in the product with the variation field. This is what we have computed before. And if you record the graphical computation we have obtained, that is equal to grad u, grad eta, so this is with respect to the integration over the Rn. So this is a region, omega is a region in Rn. And then using the area form, you can rewrite this as an integration over sigma, grad u, grad eta, d mu sigma. And what is this? This is exactly what we have computed here. This is the divergence of V. So you get an intrinsic expression here. This is negative, indeed. Divergence with respect to the induced metric, V of the variation field, d mu c, sigma. Okay. Any questions? All right. And recall that by the divergence theorem, if you integrate the tangential part of divergence of the tangential part of the vector field, that is equal to 0. So recall divergence of Vt is equal to 0 because that is equal to the boundary of V times the outward unit normal, which because of the compactly supported vector fields, that's equal to 0. And so you are only integrating the normal part. If you rewrite it, the divergence of sigma is V in the product with n times n. And then use the product rule. If the derivative is hitting the first component, because you are taking the induced metric, so the gradient is going to be projecting to the induced submanifold on the tangent space. Obviously, when you take in the product with n, that's equal to 0. So when you take the derivative, the product will only give you the derivative landing on the second part, the second factor. So that's equal to V n divergence of n. And we get this little nice expression. Negative divergence, the unit normal. And then V. But recall that by definition, the mean curvature vector, there's a sign change that we talked about last time. So I'm writing in the previous page now. This is equal to the mean curvature vector is equal to the mean curvature scalar. So this mean curvature vector equal to the mean curvature scalar times negative the gradient. Oh, sorry, the negative the normal. So you have that the mean curvature scalar is equal to the divergence normal. Now with this expression, also test it with any arbitrary vector field. So say eta again in C compactly supported test function, and you take the test vector field to be V equal to eta times EI, where EI is a Euclidean base vector in the Rn+1. Of the normal basis. So let's test it using the, so from here we see that the first variation formula is actually equal to the integration of the negative of the divergence, right? So let's take this formula out. Is equal to negative of divergence of B. So these are all integration on the induced metric. When you test it with this special vector field, you get H eta EI is equal to negative divergence of eta EI. Again, when you hit the constant vector, the derivative of constant vector is 0. So you only have, by the product rule, you only have derivative on the eta part. And this gives you gradient of eta times gradient of xi. So xi is the coordinate function in Rn+1. And the gradient of xi is equal to EI. But since here is only the tangential part, so you can take the tangential part in the second factor too, right? And then by divergence theorem or integration by part, you can put the divergence to the other side and you regain a Laplacian. So this is Laplacian of the coordinate function. So what does this mean? So this expression gives you that this is true for any eta. This is holds for any eta. Which means that when you take the H inner product with EI, you get the ith component of H. And that is equal to the ith component of the Laplacian of the position vector. And this is true for any I from 1 to n+1. So this gives you that the mean curvature vector is actually equal to the Laplacian using the induced metric operating on the position vector. So our mean curvature flow equation which is equal to d dt of the position vector equal to the mean curvature vector. Now you can represent it, rewrite it like a heat equation. But the Laplacian is with respect to a changing metric. So this is a heat type equation. So if people know what is harmonic map heat flow, the harmonic map heat flow is the equation that is compare with respect to a fixed metric. And the evolution of the harmonic map heat flow is actually slower than the evolution of this mean curvature flow, because the harmonic map heat flow is with respect to a fixed metric. There's only diffusion effect here. And when you're taking the Laplacian with respect to a changing metric, it's like adding some reaction terms. So this is a diffusion reaction equation. So short time existence is somewhat like a diffusion effect. So you have just like the heat flow, that it has local smoothing for the mean curvature flow as well. But in the long time, this reaction effect is going to dominate. And so as you can already feel, the mean curvature flow is a gradient flow of the area. It tends to make the metric to shrink. When it shrinks, the metric shrinks, then the derivative with respect to the shrinking metric become larger. So actually evolving faster and faster. So I will leave you as an exercise. We already showed that. So round spheres become extinct in finite time in mean curvature flow. But if you evolve a round sphere under harmonic map heat flow, it's not going to shrink to a point in finite time. So it's going to shrink to a point in infinite time. In harmonic map heat flow. Okay. Any questions? Okay, so let's get one more computations using this intrinsic metric. Example. So let's consider this ambient function. It has a geometric meaning indeed. So f of xt equal to so this vector, this ambient function is equal to 0 on a shrinking sphere. Right. Recall that r squared is equal to -2nt for a shrinking sphere in the previous examples that we computed in the first lecture. Now for any evolving metric, say sigma t is mean curvature flow, evolving by mean curvature flow, and we compute the heat operator. So these are intrinsic heat operator, sigma t, acting on F. But recall that the d over dt is equal to partial over partial t of f plus h df. Let me move this leftward a little bit. And the Laplacian is equal to the divergence of the gradient, both with respect to the induced metric. And then you can take out the full gradient plus divergence of the, let me move this leftward a little bit more. So this is equal to df projected to the normal part. And then you take out d dt of f, the first and the third term. And the second term is h inner product, the mean curvature inner product with the full gradient of df. Right, recall that divergence of the unit normal is the mean curvature. And this is actually, again, equal to, so you have a negative sign here. Sorry, you have a negative sign here, which means that you have a negative sign here. So this is minus negative h df. Oh, you don't have a negative sign here. But the mean curvature vector is equal to the negative of the scalar times the normal. So you have you gain back a negative sign times the mean curvature vector times df. So this cancels out. And then when you compute the partial t, you will get 2n. And when you compute the full gradient, this is equal to 2 times x minus x naught. So if you take so this is the position vector. So if you take, these computations are independent of the choice of the coordinate function. So if you take the first n coordinate to be the orthonormal coordinate on the tangent plane, and en plus 1 to be the normal vector at a given point. So you see that ddxi of the first n component give you 1. So this is 2n minus 2n equal to 0. So actually this is true for any evolving submanifold of the mean curvature flow, that you have the heat operator acting on this function is actually equal to 0. So let me give you a interpretation of this by applying another version of the maximum principle. In this case, we call it the weak maximum principle. So if you have a sigma t evolving by mean curvature flow, and such that f is an ambiently defined function. So say u is in Rn plus 1, such that it satisfies this heat type inequality. For any vector field. A is a fixed vector field. A is a vector field. Time variant vector field in Rn plus 1. If you satisfy this heat type inequality, so here it doesn't really matter whether d dt or partial t, because by definition, you will get a H inner product with a gradient of f, which is going to be absorbed into this second term as well. Then the maximum principle is going to tell you that the maximum of f at time sigma t is going to be, in this neighborhood, u is going to be less or equal than sigma 0 u. And also the boundary of u. So let me draw a picture here. So say this is your u, and you have an interval. So at any interior point, the function is going to be, so it wouldn't have any interior maximum point. And the maximum point can only happen at either the initial data here or at the boundary of the neighborhood. Okay. And then let's apply it to the example that we have computed here. For this spherical test function. Apply it to d dt minus Laplacian of x minus x naught square plus 2nt. We have computed that this is actually equal to 0, so it satisfies conditions of the maximum principle. And if it is initially greater than 0, that means the initial data is going to be, so that means the initial data is going to be contained in a ball, right? So you compute d dt minus. So constant is not going to matter. So if this is initially greater than 0, that means sigma 0 is contained in the ball of radius R0. And the maximum principle is telling you that for all later time, this is also a greater than 0 because it's greater than the initial time. So for all time, it's going to be contained in the ball. Then sigma t is going to be contained in the evolving ball, because x minus x naught square is always less or equal than r squared minus 2nt. And the converse is also true. If it is initially lying outside of the ball, then it will stay outside of the shrinking ball for all later time. Okay. Any questions? So now let's study a more sophisticated example of the mean curvature flow. So the entire graphical flow. But this is the first non-trivial examples that the flow has long time existence. So we are going to use the weak maximum principle here. To show that entire graphical solution stays entire graphical for all time. And it has long time existence until time go to infinity. Want to show graphicality is preserved. All right, so let me record some computation of the geometric quantities here. So because I don't want to get you lost by doing too much computation here. So these computations are already in the lecture note. So you can check that for the proof. So if you compute the evolution of the normal vector, that should be equal to the induced gradient of the mean curvature vector. And we define a new function v to be this unit normal vector in the product with a fixed vector field. Constant fixed vector field. So W is in Rn+1, the fixed vector field. So without loss of generality, you can just choose W to be the n+1 vector, n+1 basis vector. What does it mean to be an entire graph? So sigma 0, entire graph. It means that grad u is less than infinity at any point. Right. So if you use the graphical expression, sigma 0 equal to x u in Rn+1. This special function v, you can compute that. It's actually equal to 1 plus grad u squared. And by the evolution equation of the unit normal, and w is a constant vector, we can compute the evolution equation of this v. So again, the computation is in the lecture note. So I don't think it's a good idea to write down all this computation here, since some of you might already get lost. And it wouldn't help you too much to expose you to too much of these computations. V is equal to Laplacian induced matrix of V minus A squared V. So recall that we are writing these equations using, we all try to write it as a heat type equation in order to apply the weak maximum principle to tell us something about the geometric meaning, right? And recall that the computation we had before about that special test function r naught square minus x naught square minus 2nt is equal to, let's move it leftward a little bit. So this function satisfies the heat operator acting on it is exactly 0. Right. So let's denote this heat operator to be d dt minus Laplacian. So you have the product rule. The heat operator acting on the product is equal to F times Lg plus G times Lf plus 2 grad F grad G. Right. So with this, you can compute that. So we want to compute the evolution equation of this product. So the product V times this spherical function So the computation is again in the lecture note. I'm not going to write down all of them. Otherwise, it will take up another half an hour. It will again satisfy the weak maximum principle. Okay. So what does this tell you? So as a consequence, so at time t, v of xt times the r naught square minus x naught square minus 2 nt is less or equal than the supremum at time 0. Times, so at the time 0, you get t equal to 0, and this is a positive function. So you can get rid of that negative term. So you have r squared. In other words, 1 minus r naught squared. So actually, this is, if you think about it, this is actually not a direct application of the maximum principle. So we are considering it in a shrinking ball. So let's see, say this is the time direction. So at 0, this is BR0 at t equal to 0. At time t, you are considering U to be the shrinking ball. So at any time t, by the maximum principle, this is actually equal to the So the function v times this spherical function, as we said, it satisfies the condition, the weak maximum principle. So it's less or equal than the initial data plus the supremum on this boundary. But on this boundary, because r squared is equal to 2nt, so at this boundary is equal to 0. The value of this function is equal to 0 at the boundary. And it's positive everywhere, which means that it's less than the initial data, the maximum at the initial data. Okay. Any questions? Let me know if I go too fast or any unclear point.
The product at the top have a squared on the v times.
Let me check. Right, there's a square there, but yes. And then you will have a power to the 4 here. And then again, when you divide it, it's again the square. Okay.
Thanks.
I mean, adding the square is actually, so you want this, you multiply by this test function to get some concavity. I mean, getting higher power gives you some concavity so that it actually satisfy the desired inequality in the maximum principle, right? So you want the heat operator acting on it to be greater or equal than 0 for the maximum principle to be applicable. If it does not, you multiply by some more concave function to make it satisfying the sign that you want. Okay. Any other questions? All right. Yep. All right. Although I'm not going to do this computation, but I still have to list it out because we are going to use this later. So the evolutions of some other geometric inequalities, the computations are already included in the lecture notes. Okay, so evolution of some other geometric. Okay, inequalities. I think I haven't finished the previous example, so what the conclusion? So I have to write down for the previous example. So this is the conclusion that we decide, right? Graphicality is preserved. Okay, so let me postpone to explain a few more sentences in case there's confusions here. I mean, how do you get this graphicality? So say initially, this is let me erase this first. So initially, this is a graph. It might not have uniform gradient bound, but on any compact set, it has gradient bound. So by the conclusion here, for any later time t, for any xt on the graph, on the support of the flow, you can choose r naught squared to be greater than, say, 2 times x minus x naught plus 2nt. And then this term is going to be less than 1/2. So you have v is going to be less. So v times 1/2 is going to be less than, xt is going to be less than the maximum inside the ball at time 0, v of x naught. And recall that this v is what? Is 1 plus grad u squared. So you have at any later time, grad u is also less than some finite constant less than infinity. Okay. By choosing large enough r naught. So for any later time, you can compare with the initial time by choosing a large enough r naught. And that gives you at any later time, the gradient is also less than infinity. Okay. So this is, as we said, also another interpretation is that entire graphical solutions exist for all time. And there's no singularities for mean curvature flow of entire graphs. Okay. Okay, so evolution equations of some other geometric quantities. So by the first variation formula, you have the evolution of the area form. So it's actually equal to the mean curvature vector times negative the mean curvature vector times the test field. But the test velocity field is mean curvature itself, which means that you have negative h squared. This is the area form. And evolution of curvature. This is very important. So the full curvature is the second fundamental form. So you have it also satisfy heat type equation. But these are tensors. So H is the second fundamental form. And when you take trace of this equation, the trace of the second fundamental form is the mean curvature. So taking trace, you have ddt of the mean curvature, evolution of mean curvature under this intrinsic heat operator is equal to a squared h. So these are all having some signs that you like if you look at these equations. well, there's another one that I want to write down. So the evolution of the metric. So these are all included in the lecture note. But this will be, we will also use it at some later point for applications. All right. So the evolution of the induced metric is equal to -2 times the mean curvature times the second fundamental form. And combining these two, for any delta greater than 0, you have Hij minus delta Gij is equal to so as you can all see, these equations all somehow satisfy the right sign for the maximum principle to be applicable. For the scalar ones, you can directly apply the maximum principle. But for these tensor ones, so these are tensors, metrics are tensors, and second fundamental forms are tensors. And we will state here a tensorial maximum principle that apply to these tensor equations that satisfy such a heat type equations. So this is due to Richard Hamilton. So let me find out the expression. So sigma t again is mean curvature flow. And you have Mij, symmetric matrices. So these are all satisfied by the second fundamental form matrix and the metric matrix. They're all symmetric matrices. And such that it satisfies this heat type equation, inequality, heat type inequality, Mij Laplacian. There's some other term that are semi-positive definite symmetric matrices. And so this inequality here is understood as a semi-positivity. So we say a matrix is greater than a B matrix if and only if Aij minus Bij is semi-positive definite. So this inequality is interpreted in this way. Then the tensorial maximum principle tells you that if Mij is positive semi-definite at the initial time, then at any later time, it's also positive semi-definite. So we can use this tensorial maximum principle and the previous weak maximum principle to say something about these evolution equations, right? So as a result of this tensorial maximum principle, so you see the second term here is obviously greater than 0. If initially So let me write on another page. So as a consequence, if Hij is positive, semi-definite, geometrically it means that initial surface is convex. Then at all later time is also convex. And also mean convexity is preserved. This is just a consequence of the weak maximum principle. Right, so this is greater or equal than Laplacian of H. So mean convexity also preserved. Along the flow. Okay. Any questions about the explanations?
Mean convexity.
Oh, mean convexity means that H is greater than 0.
Thanks.
Mm-hmm. All right, so these are the consequence of the several maximum principle applied to the evolution equations of geometric quantities. So now, and we have used it to describe the evolution of graphs, but that is not interesting enough because it doesn't have singularities. And for mean curvature flow of closed surfaces, singularities are inevitable. And in order to analyze the long time behavior, we need to do singularity analysis. And the most important rule, I mean, the starting point of doing singularity analysis is the so-called Huysken's monotonicity formula. And we are going to introduce that and use that to do singularity analysis. All right. Huysken's monotonicity formula is the important tool. So there will be inevitable singularities of mean curvature flow. And then we want to understand how the formation of the singularity is and how the asymptotic behavior of that singularity is. And this monotonicity formula gives you that the asymptotic behavior. So let's denote rho of x naught t naught to be the n-dimensional backward heat kernel. Which is equal to centered at x naught t naught. This is equal to 1 over 4 pi t naught minus t exponential for any t less than t naught and x in Rn plus 1. So rho is from Rn plus 1 times R to R. So this is the n-dimensional heat kernel, but you are viewing it as an ambient function in the n plus 1 dimensional space. Right. So let's do some basic computations of this first using the induced metric. So we have done quite a lot in the first half of this lecture. So recall that the evolution, the area form that we mentioned earlier, this is equal to negative h squared times the area form. And you can compute the partial derivative of this heat kernel with respect to T. So this is partial T. So you don't need to care about the inner product with the H. So you just compute the derivative with respect to T. There will be two terms. So these two terms, if you write it down, so this x naught, t naught are some center point in the space-time for the heat kernel. So you are considering a heat kernel centered at some space-time x naught, t naught point. Also, you compute the derivative, spatial derivative of rho x naught, t naught. That is equal to the position vector over t naught minus t times rho. So what is the monotonicity formula? The monotonicity formula is about the integration of the backward heat kernel on the evolving manifold by mean curvature flow. So with the previous computations, this computation is actually quite easy now. The backward heat kernel, xt d ct. So you put it into the derivative into the, so notice that we are using ddt here. d dt of rho plus rho times d dt of the area form. And d dt of rho is equal to partial over partial t of rho times the grad rho and the inner product with the h plus this is negative rho h squared, right? And we have already computed the gradient and the time derivative. So let me know if I go too fast, okay? So you plug in what the computation here is into here. You get, they all have a common factor rho. So you take that out. Rho of x naught, t naught. And then there are several terms. Terms that are coming from the time derivative here. N over these are time derivative terms. And you have spatial derivative terms in the product with h. So you get h, sorry, this is x minus x naught over, you have a negative sign because this is a negative sign. Inner product with h, and then minus h squared. So these are all the 4 terms that you get. So you try to complete the square. You want a sign to be, you want some positive sign that you like. Rho of x naught, t naught. You have negative h squared minus x naught over t naught minus t dot h minus x naught square. So this is going to complete a square. And the remaining term, because there's you don't take the 1/2 here, so there's another half that you want to add back. So that would be rho times a positive term, t naught minus t h plus rho times n over the first term. This is the first term. And you take, this is the square term. So again, we are going to apply the induced metric computation that we had before. So what do we have before? So this term. This is a term that we don't really like. So let's take this out. The term rho times x minus x naught. So this is a vector field, and you take inner product with h with respect to the induced metric. That is equal to the divergence of the vector field. So recall that this is the formula that we have, right? The first variation formula a few pages ago. And after you compute this divergence out, it's equal to rho of x naught t naught. You have tangential terms because these are all induced metric. Tangential part square right. So the first variation formula actually have a negative sign. So the inner product of the mean curvature vector with the test vector field is equal to negative the divergence of the test vector field. So you have negative sign here and negative sign here. All right, so when you plug this in to the previous equation, so this term is going to cancel out this term. And you have a tangential part. So the tangential part is going to cancel out the tangential part here. And recall that mean curvature is always in the normal direction. So it doesn't change anything if you add the normal part here. So x minus x naught t square is equal to x minus x naught square minus the normal part. By the Pythagorean theorem. So after this term is cancelled out, and the remaining term is still a complete square. So you get a complete square. Is equal to, so let's copy this down here. So it's negative h squared minus 4t naught minus t. But now you only have the normal part. All right. And then there's the third term, which is the normal part in the product with the product term. So this is actually when you complete the square, common factor rho is still here. You have negative rho h minus x naught perp square. Sorry, there's no square in the, when you complete the square goes outside. Okay. So this is the right-hand side having a negative sign. Right, so let me correct it. When you complete the square, this is x minus x naught perp. So you have a negative sign on the right-hand side. That tells you that the integration of this backward heat kernel is monotonically decreasing. This is the Huysker's monotonicity formula.
You not want a plus sign after the h, so h plus x minus x naught perp?
Right, you're right. These are all negative, so you get a plus here. Thank you. Is monotonically non-increasing. So it might be constant. It doesn't rule out the constancy yet. It's constant if and only if this is non-increasing. And constant if and only if along the flow this elliptic equation is satisfied. So this is a special equation that we call self-shrinkers, because any flow that satisfies this equation will evolve by self-similar shrinking. So let's see that. So the mean curvature vector is actually equal to the velocity vector under mean curvature flow. And the velocity vector now is equal to the position vector so the normal velocity vector is equal to the normal part of the position vector divided by 2 times t naught minus t. So you can view that the velocity vector is actually equal to the position vector. and which means that if you consider the flow of such surfaces satisfying this equation, it will satisfy sigma t equal to, so there's a negative sign here. Right. Because so at any time t, it's a rescaling of the negative time -1 slice by the factor time negative t. So if you differentiate this position vector, you will get right. So you get a negative negative 1/2 times the, so you differentiate, there's a negative sign here. So you have -1. So you get a negative, so without loss of generality, this computation is taken with respect to x0, t0 equal to 0, 0. So when you differentiate the position vector in this shrinking solution, you get exactly the same factor out. It's proportional to the position vector. The velocity vector is proportional to the velocity vector, and divided by -2 times the time. Okay. And this is telling you much more, because so this being constant is equation first. So the monotonicity formula tells you if it is constant, then it's going to satisfy this so-called self-Schenker equation. So let me make this definition first. A self-Schenker is a hypersurface satisfying h plus x minus x0 over 2 equal to 0. So you are taking the so x0 t0 are arbitrary, right? So you are taking the x0 to be the spatial 0 origin point without loss of generality. So this is going to be the time -1 slice of a self-shrinking solution. So at time t is equal to time -1 slice rescaled by square root of -t. And we call the -1 slice to be the self-Schenker. And other slices are just rescaling of the time -1 slice. Okay, now we can apply this to do some singularity analysis. So the idea is that by this monotonicity formula, any space-time singularity, if you zoom in, is going to be asymptotically look like a self-Schenker. Now, suppose x naught, t naught. Any questions with respect to the previous things yet? If you do, let me know. Okay, so x naught, t naught, say, well, let's focus on singularities. So let's say this is a singular point. I mean, any point you can consider. So let's focus on possibly singular point. So by the monotonicity formula, we'll actually recall that mean curvature flow is invariant under space-time translations. So you can always do a space-time translation or rescaling to move this point to 0 to make our life easier. Move the point that you want to study to space-time 0. Okay. And if you integrate the Huisken monotonicity formula, so the way that we wrote it is in an differential expression. So you get for any, say a less than b less than 0. So you want to study the space-time 0 point. And if you integrate the Huisken monotonicity formula, you see that sigma b rho minus sigma a time a rho. This is equal to integration from a to b. And then the right-hand side, h plus x perp over 2t squared. So this is the integral form. So if the backward heat kernel is with respect to the center point space-time 0, so we will omit this subscript for simplicity. So now because of the monotonic decreasing, say this is 0. So we want to zoom in around 0. Okay. So now for any a and b, and choose a sequence of lambda I going to infinity. So recall that we can parabolically rescale a mean curvature flow to obtain another mean curvature flow. And here we want to parabolically rescale a flow with respect to a point that you want to study. In this case, is 0, 0. So first, by the monotonicity formula, this rho is monotonic decreasing. So as lambda I go to 0, up to pass to a subsequence, sigma b over lambda I square times slice a over lambda I square rho. This is going to 0 up to subsequence of lambda I. So because both B over lambda I square and A over lambda I square are converging to 0. This is A over lambda I square. And this is a monotonically decreasing property. So the difference, if you pass to a subsequence, you can find a subsequence such that this difference is converging to 0. Okay. And now we parabolically rescale the flow. So by this sequence, so parabolically. To get a new sequence of flows. So we denote mi to be sigma I t. This is a new sequence of flows, which is obtained by parabolically rescaled by factor lambda I. Right, recall that we have defined this parabolic rescaling in the first lecture. So this sigma I t is equal to lambda I. You scale by, so the scaling in the space is the square root of the scaling in time. This is why we call it parabolic rescaling. Right. This is how the parabolic rescaling is defined. So now for this new sequence of flow, let's compute. Now, if you integrate for any AB, A less than B less than 0, the rescaled flow, sigma IT, rho of H minus X perp over 2T, sigma IT. So by the integral form of the monotonicity formula, so this is the integral form. So you can rewrite it as the difference on the left-hand side. So this is equal to sigma IB rho XB minus sigma IA rho XA. And because these are rescaled flow, so let's rescale it back. Okay. So by definition, this is lambda I of sigma I BI over lambda I square rho. So you rescale it to write it as integral over the unrescaled flow at time A over lambda I square. So when you rescale it, you get rid of the lambda I. So you get, sorry, here. So by definition, this is equal to sigma T sigma B over lambda I square, sigma A over lambda I square. So the rescaled flow by definition is the parabolic rescaling of the original flow, by definition. you scale it back, you get b lambda I square of rho of, now you have to rescale the lambda I x, then b. So when you have rescaled that, because the volume form also changed by a factor of lambda I, so there's another lambda I to the power n, the volume form change as well. Now you are integrating, this is over the IB, but when you rescale it back, so this is sigma b over lambda I minus So let me write clearer about this point. So you are integrating sigma d lambda I squared. Right. But we have already deduced that up to a subsequence, this is converging to 0. Okay. So if you get rid of the lambda I in the the heat kernel, if you rescale it by the lambda I, so you can get rid of the lambda I factor here. So if you recall what is the heat kernel, it's actually 4 pi t to the power n minus 2. So if you scale both the space by lambda I and the time by lambda I square, so this part is invariant. But if you scale by time by lambda I square, that's going to cancel out this term. And this is going to give you lambda I square rho. Now it's x b divided by lambda I square. And you get rid of the lambda I to the power n. Again, a over, at the time, a over lambda I square. A over lambda I square. Okay, so this is up to passing to a subsequence, as we have deduced that up to passing to a subsequence is converging to 0. So this is converging to 0 up to subsequence, which means that this sequence of rescaled flows, this is a non-negative term and it's converging to 0, which means that sigma IT, when restricting to the space-time neighborhood, r to the n plus 1 times any AB. So A less than B less than 0. Converge to a self-shrinking solution in a weak sense, measure theoretic sense. So these are integrals, so you get weak convergence. All right. So because it's positive, rho is also positive. So this h minus x perp over 2t has to converge to 0. And if it is 0, then it has to be a self-shrinking solution that we talked about before. Okay, any questions? Okay, so there are several remarks that are necessary. So although this looks good, but it might not be as good as you expected because it's a measure theoretic convergence. You don't really have any control like in geometry or topology on the convergence. Okay. And for example, you might be converging to some high multiplicity of a shrinker in the measure theoretic sense. And the convergence might not be smooth or in any CK. So we will get to that. And the second point is that, so we have, if not emphasized, but we have said that we have to pass to a subsequence, right? So there are some requirement that you're required to there's some conditions that you need before you take a subsequence, some compactness theorems. So we will get to that. There's a compactness theorem that guarantees that you can take a subsequence. So this is a Brachi's compactness theorem that we may or may not get to in the next lecture when we talk about weak flows. So you pass to a limit in the weak sense as a measure theoretic sense. I mean, the space of measure usually have very good weak compactness property. And because it's passing to a subsequence, so when you obtain such a limit flow, so sigma I, sigma IT converge to a limit flow, which is self-shrinking. But this limit flow, so you call A limit flow. You don't call D limit flow because it might not be unique in general. It might depend on subsequence. On the choice of subsequence. Okay. Any questions up till now? There are several cases we will mention that we do know the uniqueness of this limit flow. So we will get to that a bit later. So let me make another definition. So in this special case, when you are just zooming in at a fixed point, so in general, you can take limit flow for any sequences of Brachi flows, and x0, t0 might not be a fixed point. But if you fix a point to do this parabolic zoom in, so definition, tangent flow. So again, a tangent flow at x0, t0. Right. A tangent flow at x0, t0 is a subsequential limit, depend on subsequence you choose, of this parabolic rescaling, but you fix a point. So d lambda I of sigma minus x naught t naught. So you move the point that you want to study to space-time 0 and move the space-time track of the, so you move the space-time track in space-time so that the point you want to study is moved to 0, and then you parabolically rescale it. So this is defined in the first lecture again. This is it has a little flow. Let's call it sigma subscript infinity. So a tangent flow, as we said, it always has to be a self-shrinker weakly. So asymptotically, at least in the measure theoretic sense, a singularity, the formation of the singularity is going to be look like a self-shrinker. So why do we call it formation? Because this is just a backward rescaling. So when we are doing all this, we are considering, remember that we require that a less than b less than 0. So we are only zooming in at the sequence point backwards. So we are zooming in small neighborhoods here, which is a over lambda I square, b over lambda I square of the space-time track of a flow. So you zoom in this. When you zoom in by lambda I square, you move it to parabolically rescale it to A and B. So you rescale the flow so that it's defined in A and B, this new sequence flow. And this limit flow is going to capture the asymptotic behavior as the flow approach the 0, space-time point. So it captures the formation of the singularities. So there are, so this is what Huysken's monotonicity formula can tell you. First, you can only know about the backward in time. So well, people have believed that there is a forward singularity, forward monotonicity formula tells you that the forward asymptotic behavior, but I believe that is not rigorously proven for general cases yet. So backwardly, the formation of singularities asymptotically look like a self-shrinker, and it is believed in general, that the way that you flow through a singularities. So you form a singularity here, but there are if there are some things still left, you want to flow through a singularity, it is believed that it's going to be asymptotically look like a self-expander. But there's no monotonicity formula telling you rigorous that yet. Okay. Right. In the last 8 minutes, let me bring up the notion of type 1 and type 2 singularities. So we will use that to analyze the flow of convex hypersurfaces in the next lecture, which we don't seem to have time to get to at this lecture. So we call a singularity type 1 if T naught minus T of the second fundamental form, supremum, is less than C less than infinity. So it tells you that the blow-up rate of the second fundamental form is at most square root of T naught minus T of that order, big O of that order. So it means that the formation of singularity is not too fast. And also we call it type 2 if it is not type 1. Okay.